Hey everybody, welcome back. Heart, how are you doing?
I'm doing wonderfully, so excited to join you.
So why do atoms even bond in the first place?
It's all about stability. They're trying to get a full outer electron shell.
Like a full set of electrons.
Exactly, we call that the octet rule.
Octet, so 8.
For most atoms, yes, 8 electrons in their outermost shell.
But not all.
Right, hydrogen, helium, they just need 2. That's a duplet.
Oh, so smaller atoms are different.
Exactly, they're seeking that stable configuration.
And how do they do that?
3 main ways: they can gain electrons.
Or lose them?
Yep, or they can share them.
Like sharing toys.
Pretty much, they're basically just trying to be happy and chill.
So it's about reaching that perfect number of outer electrons.
That's the whole game. Once they hit it, they're super stable.
No more reacting then.
Not as much, they're content.
So Lewis dot structures. What exactly are they and why are they so crucial?
They're a super simple visual way to show valence electrons.
Valence electrons, the outermost ones that do all the work.
Exactly, the ones involved in chemical bonding.
And G.N. Lewis came up with this idea.
Yes, Gilbert Newton Lewis in 1916. A really foundational concept.
How do they visually represent these electrons?
You draw the element symbol, then place dots around it. Each dot is a valence electron.
So oxygen would have 6 dots around it.
Spot on, because it has 6 valence electrons.
And these dots help us understand molecules.
Absolutely. They're key to building and understanding molecular structures.
Like how atoms connect.
Precisely. They show how atoms share or transfer electrons to form bonds.
So we can see the blueprint of a molecule.
That's it. It's essential for predicting molecular geometry and reactivity.
That's a lot of power from just a few dots.
It really is. So simple, yet so incredibly insightful.
So chemical bonds, what are the main types?
There are 4 big ones.
Oh, really?
Yeah, ionic, covalent, metallic.
And one more, right?
Coordinate covalent.
Okay, ionic first. How does that one happen?
That's literally electron transfer.
Like giving an electron away.
Exactly. One atom hands it over.
To the other.
And then they're charged and attract. Simple.
Got it, covalent then.
Sharing electrons equals sharing.
Not giving at all.
Nope, they team up on a pair.
So like in water.
Precisely. Then there's metallic bonding.
What's that like?
It's a sea of electrons.
A sea like everywhere.
Yes, they're pooled, delocalized.
Ah, that's why metals conduct.
You got it, electrons move freely.
And the last one, coordinate.
Unequal sharing. One atom donates both.
So one atom is extra giving.
That's the one. It contributes both electrons to the bond.
So with covalent bonds, are they all the same strength? Or are there different types?
Oh, great question. There are actually 3 main types: single, double, and triple bonds.
Wait, really? What makes them different?
It's all about how many electron pairs the atoms decide to share.
Okay, so a single bond is one pair then.
Exactly. Just one pair of electrons, so 2 electrons total, being shared between 2 atoms.
And double bonds.
You guessed it, 2 shared pairs of electrons. That's 4 electrons in total.
So like between carbon atoms sometimes.
Yes, perfect example, like in an alkene. And then triple bonds are 3 pairs.
Whoa, 3 pairs, so 6 electrons.
Precisely, 6 shared electrons. These are the strongest and shortest of the covalent bonds.
Strongest, that makes sense. More electrons holding them together.
Right, think of it like multiple rubber bands. More rubber bands, stronger connection.
Got it, single, double, triple, based on shared electron pairs. So the octet rule sounds like a fundamental law. But are there ever times it doesn't quite apply?
Oh, absolutely. Nature loves to throw in some curveballs, even with something as core as the octet rule.
Wait, really? What kind of exceptions?
We have electron-efficient compounds first. Think boron, it's often stable with just 6 valence electrons.
Only 6, not 8. That feels wrong.
It can be. And then there are hypervalent compounds, where atoms actually have more than 8 electrons.
More than 8. How does that even work for stability?
Elements in the 3rd period and beyond can use their d orbitals, like sulfur hexafluoride, SF6.
Okay, SF6, got it. So what about ions in Lewis structures? How do we show their charge?
That's actually pretty straightforward. We just add or remove electrons to get the correct charge.
And
Then you put square brackets around the entire Lewis structure, with the charge written as a superscript outside.
brackets and the charge. Simple enough. So it clearly shows the overall charge.
Exactly. Even with these exceptions, Lewis structures adapt to give us a clear picture.
So let's put this into practice. Take something simple like in a Cl common table salt. How does this all apply?
Perfect example. Sodium has one extra electron it wants to lose.
And chlorine needs one, right?
Exactly, so sodium gives an electron to chlorine. Transfer complete.
And they're both instantly stable.
Boom, ionic bond. All about that electron transfer for stability.
Okay, what about something like CO2, carbon dioxide?
There, carbon and oxygen share electrons. Double bonds, super strong.
Sharing for stability,
Always, they're each trying to fill their outer shell, like CH4 methane.
where carbon shares with 4 hydrogen atoms.
Right, 4 single covalent bonds. It's just a different way to reach that happy, stable state.
So no matter the type of bond, giving, taking, or sharing,
It's always about the atoms wanting to be stable. That's the core driver for everything.
well, that brings it all together nicely.
It really does.
Thanks, Hard.
Thanks for having me.